Now, let us introduce the advanced oxygen and hydrogen generation system, an innovative solution for the most cost-effective production of oxygen and green hydrogen from fresh water, designed for both space missions and terrestrial applications. To obtain a continuous supersonic highly superheated steam jet, a stoichiometric binary mixture of oxygen and hydrogen, blue arrows, is fed into the annular detonation chamber through injectors, where it is diluted with primary low-parameter steam with a temperature of 100 to 150 degrees Celsius. At the same time, heated feedwater, red arrows, is injected from the internal volume of the cooling container through Hulse turbulators into the annular detonation chamber, where it is converted into primary steam to form a stoichiometric triple mixture of oxygen, hydrogen, and steam, which is ignited by the ignition system using spark plugs. In the annular detonation chamber, continuous detonation combustion of a triple stoichiometric mixture occurs with the formation of a high-frequency continuously rotating detonation waves, that leads to detonation compression and superheating of steam to temperatures of about 2000 degrees Celsius with the formation of a supersonic superheated steam jet. At the same time, longitudinally pulsating detonation waves are generated, which propagate along the detonation channel and enter the outer annular conical cavity of the cooled gas dynamic resonator, made in the form of a Laval nozzle, from which they are repeatedly reflected. The multiple reflected detonation waves interact with the leading longitudinally pulsating detonation waves, implementing the process of multiple shock resonant compression of steam. In a detonation superheater, tangentially and counter-connected to a vortex reactor, a continuous supersonic jet of a mixture of hydrogen, oxygen, and highly superheated steam at a temperature of about 3,500 degrees Celsius and above is generated, accompanied by resulting shock detonation waves that tangentially enter a centrifugal vortex reactor, where, under the action of centrifugal forces, radial stratification of the jet occurs, which is divided into two streams. Lighter hydrogen molecules are collected in the central part of the centrifugal vortex reactor and are tangentially fed to the hydrogen vortex cooler, where they are cooled. Further, the cooled hydrogen stream is fed to the Sabatier system or another consumer. Heavier oxygen molecules are collected in the peripheral part of the centrifugal vortex reactor and are tangentially fed to the oxygen vortex cooler, where they are cooled. Further, the cooled oxygen stream is fed to the lunar module life support system or another consumer. The resulting steam condensate is simultaneously removed from the oxygen vortex cooler and the hydrogen vortex cooler through a common condensate removal system and returned to the AOHGS. Further, the supply of starter hydrogen and starter oxygen is stopped, and part of the generated hydrogen and oxygen is supplied for its own needs. The AOHGS switches to a self-sufficiency operating mode, consuming only water from external sources. The consumption of electrical energy from external sources is minimal. External electrical energy is only needed to ensure the operation of the AOHGS control system, including the high-voltage unit to ensure the operation of the spark plugs in the ignition system, as well as to operate the pumps to ensure the circulation of feedwater in the cooling container. At the same time, AOHGS is capable of fully providing itself and the lunar module with electricity, for example using the hydrogen fuel cells, additionally consuming some of the generated hydrogen and oxygen.